to find the best W. So what does training mean? Training means finding the best W such that you can optimize some loss function. What loss function? For example, it could be the mean square loss. Right? I think some of you have probably seen the mean square loss before. You maybe take your vector y, which is your target. You subtract the output of your function. So function takes in x, takes in w. It predicts a y. You subtract that from the target. Then you take the L2 loss, for example. We spoke about the L2 is. Take the L2 loss, and maybe you square that. You sum that over all of your data points, and that gives you a measure of how good your W is. All right? So you want to find the best W that minimizes this quantity. And this is an example loss function. There's multiple loss functions that you're going to see in the practicals. And so usually, if you go look something like this, right? You have your data set. You let's say you have found the best W, and then that is kind of like a best fit over the data set that you were given. And hopefully this generalizes to new points. It looks like something like this one, generalized to new data. Okay, so I hope that gives the intuition. That kind of like says the purpose of why we need vector calculus and where that is usually applied in machine learning. So there's different types of, different degrees of scaling in terms of vector calculus. I'm sure you guys have seen scalar differentiation, right? You have a function that takes in a real number, So you have seen that. Maybe some of you have seen multivariate calculus, right? So you have a function that takes in multiple inputs. You can imagine that could be, let's say, the set of future in the like price prediction and data set. And then output a single value could be the price of that house, right? Then if you generalize all of these, you have vector calculus. So you have a function that takes in multiple entries. So it takes in a vector and out the vector values. So that's the general case. Let's call it vector because it's an output. And this is what we are going to be talking about during this section of the tutorial. Point out that in general, there's something called tensor calculus. So for those of you who have maybe an engineering background, a physics background, you have heard a bit general and those other kind of like more complex fields, usually they speak of tensors. And even in the advanced fields in machine learning, you have heard this word tensors. And just think of it as a generalization of that we just spoke of, just generalizes that. So everything I'm going to be speaking about during this tutorial actually still applies to tensors, right? It's just that like maybe there are easier ways of understanding tensors when you go take a dedicated course. And hopefully, as I move through scalar differentiation, multivariate case, and vector fields, you see how all of this natural this progression happens, and it is the same progression that happens when you then go to tensor calculus. So do not stress if you see tensor calculus anywhere in advanced papers and so on. It is pretty much the same thing you have learned here. Okay, so what is a gradient? So first, we need to understand what is derivative. And usually it is defined formally as a limit of a function as h tends to 0. So this is the formal definition. I'm going to break down what this means. So you have a function f of x. You define the derivative of f with respect to its input x as, let's say that you kind of take of x, and then you take a tiny change on x, right? Let's call that h. So then you take f of x plus h, subtract the value of f of x from that, and you divide that change that you made, h. So that is like a difference, right, between the current value and then divide the amount I have set. And then if you take that change to be extremely small, right, so as close to 0, that is what derivative means. So it's just about change. I was here, I moved here. Like, can I describe this change that just happened? So that's what the derivative means. So let's say you have this sine function, this curve here. The dotted line you can see is what we call the tangent line to our curve, right? And it's also called the derivative of our function at that point, right? That line. Then the red line you see there is as if you started at that point below, you took a very large step forward on your x, and you landed at that other point, right? That defines that line there. And then as you make that point smaller and smaller, as you make that change, h, smaller and smaller, you get closer and closer to that dotted line. and that is why that dotted line is called the tangent or the derivative of your function at that point. I hope that kind of makes sense. So that is the formal definition. From that very simple formal definition, you can derive all of these classic derivative rules that I'm sure many of you have maybe seen before. So I will maybe just focus on two of those. So the most popular one is, let's say you have x to the power n. The derivative of that is you take n, you multiply by x, and you reduce the exponential by 1, right? So the derivative of x to the power n is n times x to the power n minus 1. I hope that kind of makes sense. Cool. And then there's multiple other examples of derivatives there. You can derive all of these from that simple definition I gave earlier. So if anyone's interested in those derivations, we can talk about that in the next talk. Okay. So then from that, there is some very common rules that we usually use everywhere in calculus that again derive from the simple definition I just gave. The first is sum rule. If I have a function f of x, and I add another function g of x, and then I want to say what is the derivative of that addition, all right? Then it is the same as saying, let me differentiate f, let me differentiate g, and then add those two derivatives. Right? And intuitively, again, what's the geometrical interpretation of this? I have two functions, f and g, and then I'm saying, what happens if I add those two functions and then I do a tiny change, an infinitesimal change on that function? Where it's the same as saying, what happens if I first do that infinitesimal change on f, and I do the same change on g, and then I sum those changes. Right? So that is the intuition behind the sum rule. The product rule is a bit more interesting because now we are not doing a simple sum, we are doing a multiplication. And the rule is, you have two functions, f and g, you multiply them. The derivative of that is, first consider the change you are doing in f, multiply what you get from that change with your function g, all right? And then add to that the change in g, so that's what g prime. By the way, when you see prime here, I'm just saying it's the derivative of that function. Right? So if you see the prime there, that's the same as saying d of that function with respect to the variable, let's say dx in this case. Okay, so the product rule, differentiate f with respect to x, you multiply that by g, plus you differentiate g with respect to x, and you multiply that by f. So that is sort of the intuition behind this formula. And finally, you are going to see this used in pretty much every situation in machine learning is chain rule. Right? And chain rule is, you have a function f, you apply it to a value x, you get the result of that, and you apply another function g on that. What is the derivative of that? How can you describe the change? If you do an infinitesimal step, an infinitesimal change on x, how does this change this composite function? And the chain rule says that you first derive g with respect to the function x, because if you think of this case here, f of x is like the input variable to your function g, right? So then you are differentiating g with respect to f of x, and then you multiply that by the derivative of f with respect to x, right? The intuition here is, I am kind of asking, I have my function f of x. If I do a change in x, how does it change this function f? Then let me multiply that by, if I do a small change in f, how does that change my g? Right? So that is the intuition behind chain rule. And then you can derive quotient rule from that, but I can skip that. But it's pretty much saying the same thing, but instead of multiplication, it's division. Okay. And so these are usually kind of like different ways you will see this written. So you have the composition of two functions, g and f. That essentially just means g applied to f of x. And usually we use prime to represent differentiation. So let's maybe take an example to see how chain rule works. So let's say that you have this very simple function. G of z is equal to 6z plus 3, where z or z is minus 2x plus 5. Maybe I can kind of give you like, 2 seconds to try and see if you apply chain rule, that function that's shown above there, to this simple example, what will be the output? So you have your z. So you first differentiate that with respect to x, right? What will that give us? So if you differentiate this using the rule I showed earlier for x to the power n, it will you have minus 2x plus 5. Apply some rule to this. So then I first need to differentiate minus 2x. Differentiating that is going to be minus 2 because it will be x to the power 1 minus 1. That will give 0, right? So the output of differentiating minus 2x is going to be minus 2. And the output of differentiating 5 is a constant. When you differentiate the constant, it turns to 0, right? Because a constant doesn't change. Okay, so then if you do those two differentiations, you add that together, it gives you minus 2 for the derivative of z with respect to x. Then, so this is the more advanced example, but let's go to the simple example. So then that comes gives us minus 2. We multiply that by the derivative of g with respect to f, right? And g was what? 6z plus 3. Find the derivative of 6z, so that is just 6 times z to the power 1 minus 1. So z disappears, and you're only left with 6. 3 also disappears because 3 doesn't change, right? It's a constant. So then you multiply those two derivatives according to chain rule, and then you get 6 times minus 2, which gives you minus 12. Can I kind of have a show of hands, like if everyone is understanding this? All good? Because like this is really the key. Like, if everyone here kind of leaves understanding chain rule applied to any function, then this is a win, right? Because you're going to use that for the next practical. Okay, cool. Awesome. Then let's take a more complex example, which is this tan h. So I'm not going to go into details, but it is the same idea. You have tan h, which is a function, and you have z, which is x to the power n. You apply the rules I've just mentioned, and that gives you this complex root case resource here. And so I don't go into that into details, but it's applying the exact same rules I just explained earlier. Okay. So that was scalar differentiation. So for those who have done scalar differentiation before, I'm sure this is kind of like just a refreshing memory. Now we are going to extend that to multivariate differentiation. And everything you have learned so far applies here very easily. Yeah, there's nothing really new that I'm now going to be introducing. So if I want to differentiate y, which is f of with respect to this vector x, what does that mean? Well, now there's multiple ways f can change, right? I can change f by changing the first dimension of x, right, x1 a bit, or I can change f by changing the second dimension of x a bit, right? So I have a whole vector, a whole multiple ways that I can change f. So the derivative of f has to be with respect to one of those variables. So that is what we call a partial derivative. I'm asking how does the function change with respect to one of the input dimensions. And so that is kind of like what that looks like, where you see that here I'm deriving f with respect to xi. So I'm only changing xi by a bit. And in general, if you then ask, what is the derivative of f with respect to I, where I goes from the first dimension to the last dimension, what that gives us is something that is called the Jacobian. I've heard of Jacobian spoken of in papers. It's used a lot in machine learning. That is literally it means. It's just a vector that says how is your function changing with respect to each of the input variables. Right? Something like that. So earlier we saw a vector is something that goes vertically, but now it looks like something that is going horizontally. We call this a row vector. Right? So usually, terminology-wise, if you see something that is like a 1 by n matrix, it's called a row vector. If it is vertical, it's called a column vector. All right? Okay, so that's the Jacobian. How that makes sense? So let's take an example. Let's say you have this function here. It takes in two inputs, right? x1, x2. So you can imagine that it's a two-dimensional vector. And that is a function. So let's derive that. That is a more complex example that you guys can kind of think about after the tutorial, during the coffee break maybe. So let's derive this function, right? So I want to find the derivative of f with respect to x1. And it is defined like that. So there's multiple rules coming into play here. There's sum rule because it is the addition of two functions. There is product rule because it is x1 to power 2 times x2, right? So let's see here. So we first derive x1 to the power 2 times x2 with respect to x1. So the 2 comes down and have 2 times x1 to the power 2 minus 1. That leaves you with what? 2x1, x2. That is what we have to the left there, on your left. So 2x1, x2. And if you derive x1 times x2 to the power 3, you're deriving with respect to x1. This is the most complex thing to maybe try and understand with respect to partial differentiation. Is treating one as a constant, because the only thing you are changing other variable, right? So if I'm deriving x1 times x2 to the power 3 with respect to x1 is the only variable here now. So x2 to the power 3 is constant, right? So that is why x1 then to the power 1 minus 1, that disappears. I'm left with x2 to the power 3. So that explains what on the left-hand side. We have 2 times x1 times x2 plus x2 to the power 3. Does that make sense to everyone? Cool. I see some people nodding. And it's the same thing that we're applying to the second function there, the more advanced one, right? So if we differentiate that, we have the function x1 plus 2 times x2 to the power 3, and then so that's one function, and then the second function is taking the square of all of that, right? So then we apply the same rule that we applied before, right? And here is going to be chain rule again, right? So treat what is inside the bracket as a variable. Then if you derive this, you have 2 times what you have in the bracket raised to the power 2 minus 1. So that is why you have the result on your right-hand side. Right? Cool. And it's the exact same thing that you do for the second variable x2. So now we have the derivative of f with respect to x1. So we know how f changes if I change x1 a bit, and we know how f changes if I change x2 a bit. So then that gives us the Jacobian. Right? So the f of the x is a row vector that says how each of my variable, that is how f changes when I change each of my variables. So that is the Jacobian, a 1/2 vector. 1 because the output dimension is 1, right? The function takes in a vector of dimension 2. That is why we have 2 there, and it outputs a dimension of 1. Cool. I hope that makes sense. So now let's generalize that. Let's look at calculus. And again, it's the exact thing that I was explaining earlier. Inputs and outputs. So you have a form of internal vector x, and it outputs an m-dimensional vector, right? So how are we going to differentiate this? If you apply the same rule I've been explaining so far, hopefully you will see that like nothing has changed, right? So now I just say my function f is changing in multiple ways and it's outputting multiple things. So then I just want to ask a question. How does the first output, the first dimension of my output change if I change the first dimension of my input? How does the second dimension of my output change if I change the second dimension of my input, right? And so on. So then what you see is on the rows are basically saying how each dimension of the output is changing with respect to each dimension of my input. And so the dimensionality of that is an m by n matrix. N is the dimension of my input, m is the dimension of my output. So that is called the Jacobian matrix. And if you go like, so this is just the general way of saying it, right? The matrix at position ij is just going to be the derivative of f with respect to the first output, the derivative of f in the first output or the ith output with respect to the jth input or input dimension. So given that, maybe some of you have kind of like realized this when I showed that the Jacobian is now a matrix. Because earlier we spoke about how matrices are basically just linear transformations. Every time you have a matrix, what that matrix is saying is you're taking an n-dimensional vector and you're transforming that into an m-dimensional vector. This is just a linear transformation. And the Jacobian matrix is a matrix. I mean, the Jacobian matrix is also a linear map, right? It's taking n-dimensional inputs, outputting something m-dimensional. So then one way of interpreting what this Jacobian is and this is really important for having like a really good intuition of how generative models work and pretty much all of modern machine learning, is that the Jacobian is the best linear approximation to your function, right? Because you have your function at a given point, you find how that function changes in any direction that you change your output, then it's like a whole plane on that point, right? So have a function, you have the Jacobian. What that means is that Jacobian is kind of like the best linear approximation to your function at that point, right? That is used, that idea is used a lot in machine learning. Okay, so how that makes sense? So in general, let's say you have a function f that is just a linear map, a times x, right? We saw that x is a vector, a is a matrix. So let's say that is your function. Then it looks something like that, right? You have a at position 1, 1 times x at position 1, a at position on the bottom right, a at position mn times x at position n. So that is the matrix you get out of that if you apply the matrix vector multiplication that Ismaili just showed you. So what is the derivative of this? Intuitively, without doing all of the computations which I just spoke about, and just thinking of the Jacobian is the best linear approximation to your function. And what we have here is a linear map, right? A matrix A applied to a vector is just a linear transformation. Can anyone guess what the Jacobian of this function is going to be? Does anyone want to shout the answer if anyone has a guess? No guesses. I'm hearing people murmuring, but no one has the confidence to shout here. Perfect. Does that kind of make sense to you guys why the Jacobian is A? This function f of x is a linear transformation. It's taking A, taking the matrix A, multiplying that by a vector, right? The vector x. So it's already a linear map. So the Jacobian of that is just going to be A. The best linear approximation to a linear function is just a linear function. Cool. So in general, that is the idea. If you take anything away from this tutorial, is one, gradients speak about change. You have a vector space. You want to know how that space changes when you change your input. If your input is n-dimensional and your output is m-dimensional, you want to know how each part of that input, each dimension of the input, changes each dimension of your output. And what represents that is a Jacobian matrix. And the form of Jacobian matrix is a dimension of our target dimensions, because a matrix, again, it's taking input dimension, mapping it to output dimension. So what you expect to be the shape of your gradient, of the Jacobian matrix, is number of dimensions for the output. Here we are calling it the target if you are doing machine learning, by number of dimensions of your input. Cool. So that is going to pretty much it. I hope all of that kind of makes sense. Here I'm showing an example for machine learning. There is a of them which I gave earlier. This exact example, we are going to see it in the prac just now. So let's talk about it during that prac. If you apply all of the rules I just showed you guys, what you will get is this function here. How your weight of your neural. But that awesome. So that is it for this tutorial. I hope you remember all of the key takeaways. Gradient generates the slope higher dimensions. I just spoke about that. The geometric intuition behind that, because it's what is going to carry you throughout all of the complexities of deep learning. Thanks, guys.